Before we go through your quiz, I wanted to go over this problem that I told you to try to work on your own at home. This one's not a very difficult problem, but it does take a little bit more thought because we're not giving two things, whereas in our other examples, we really weren't given one thing. So it's just a little bit more difficult, though, again, not a very difficult problem. So we're given our two isotopes of boron, and we're going to assume that it only has two isotopes, because otherwise this problem would be a lot more difficult if we had three unknowns. And we have the atomic mass of both isotopes, and we also have the average atomic mass, which is given to us. And what we want to know is the percent abundance for each isotope. Now, one thing we need to remember is for the percent abundance, it's going to be a total of 100%. So that's a helpful thing that we already know about it. So we're given a couple of things. We're given our atomic mass. I want to write that in red. Of boron, 10. Which is, of course, near 10. Atomic mass units. We know our atomic mass of boron, 11. And then we know our average atomic mass. And looking at this one, notice the average atomic mass is closer to 11 than 10. So that's already given us an idea that the difference between our atomic mass of our average abundance of our two. We already have a little bit of information just by looking at the difference. So we're looking at between 10 and 11, and notice the number is closer to 11. That's a good indication that boron 10 is going to be in a lower percent abundance. So we already know a little bit about that. This is not really going to give us the number, but it's always good to use the knowledge that you already can get from the problem to help guide you when you're answering a problem like this that's maybe a little bit more difficult. So we know that our atomic mass is equal to our fractional abundance, or our summation of our fractional abundance of one isotope times the mass of that isotope plus the fractional abundance of the other isotope plus the mass of that times the mass of that other isotope. So we know some information there. If I were to fill this in, what I see is I'm going to end up with two unknowns. So that'll be my fractional abundance of boron 10 times our mass of boron 10. And remember, fractional abundance won't have a unit attached because it is just a percentage. It's a fraction of a whole. Now for me, I don't really work well with all these letters in my unknown, so I'm just going to switch this to x and y, because I do algebra better if I just see an x and a y. This is not something you necessarily have to do, but it just makes it a little bit more clear. So let's say our fractional abundance of boron 10 is x, and our fractional abundance of boron 11 is y, just to make our equation a little bit more clear when we're working it out. Little tricks that sometimes help with complicated equations is trying to make it as simple as possible. You kind of trick yourself if it looks more simple than it is. So this is a little bit easier to look at, even though I didn't do anything but replace x and y. So there's one thing that we do know, of course, is that my fractional abundance of boron 10 plus my fractional abundance of boron 11 is going to be equal to 1. And I know that because that's what fractional abundance just means. If I only have two isotopes, a fraction of one plus a fraction of the other is going to equal to my whole, my 1. So I can say x plus y is going to be equal to 1. And that's just applying something I already know about what a fraction is. So I can solve, I have two equations, I have two unknowns, but I have the same unknowns in both equations. So I can solve for this equation and plug it in. So therefore I'll only have one unknown in my equation. It doesn't really matter if you solve for x or if you solve for y, but I solve for y on my paper, so that's what I'm going to do here. But you should get the same answer. So if I solve for y, I will subtract both sides by x. So I see my y is equal to 1 minus x. So I can just put that into my equation, and then I'm just going to have my unknown of y, and I can solve for that because that's a lot easier to solve for. So that's my 1 equals y. I'll put that in. And now I'll just have my unknown of x in my equation. Which is why you have to be in algebra to take this class. Because you're supposed to have a decent understanding of algebra at this point. So now I only have x in my equation, and this is going to be a lot easier to solve for. So I will first simplify this by multiplying my 11.009 times my 1 minus x. And I am going to move on to my next page. Okay, I was going low there. So 1 times 11.009 minus my x times 11.009. It's my x. So remember, I can, in algebra, both of these terms have x with them, so I can add them together. I can add like unknowns. So that comes out to negative, just don't lose it. Because 10.013x minus 11.009x is going to give me a negative number. So don't lose your negative sign. Easy ways to make a mistake. I can subtract this from both sides, so I only have my number that doesn't contain x on one side of my... Yes, I'm keeping all of my numbers for now. And actually, I'm starting with, I have 5 significant figures, so I really should have 2 zeros. As of now. So when I did my multiplication, I have 5 significant figures, but now I am adding and subtracting, so that means I should have 3 decimal places. So I'm keeping that 0 for now, but I should only have 3 decimal places, so I just had it underlined. So I'm going to subtract my 11.009 from both sides. Now I know I'm not fully explaining algebra here. That is not what I'm here to do. I'm here to teach you chemistry. So if you're having an issue with algebra, please come to my office hours or go to tutoring for it. That's not the goal of this class to necessarily teach you how to solve algebraic equations, but I'm fully willing to work with you on your own if you need to. So I know I'm going through this work a little fast, but you should know it. So it only has 2 decimal places. So now to solve for x, I can divide both sides by negative 0.9960. Also note, it should come out to a positive number because it's a fraction. So if it doesn't, you probably lost a minus sign somewhere or did something incorrect. So more ways you can check yourself. You can't, if we're doing the fractional abundance, we can't have a negative number. So when I solve that, my x is equal to this fraction. Of course, it asks for percent, so we're going to multiply it by 100. Which we should only have a total of our 2 significant figures, so that should be 20%. So how much of y do we have? We have 80%. And that makes sense based on our amount. So I can either, again, go back to my x plus y equals 1, and I could plug this in. Or I can say my percent x plus my percent y equals 100. Yep. That should be what it came out when you divided both sides by... Oh, wait. Sorry. I don't know. That's just a typo. It's supposed to be... This is a 9, and it's supposed to be 19. I'm so sorry. I'm not sitting here on my calculator because that takes too long, and I'm looking down and trying to write. Sorry about that, guys. It's definitely 20%. I just wrote that wrong. I try to think about what I'm telling you, plus write it down, and look at the numbers I already calculated, so once we figure this is 20, our y is 80. And you could always double check that again because our total percent, 10.81, is closer to our B11 mass, and that makes sense that we would have more of B11. Again, if you're having issues with your algebra, please make sure to come ask questions, and there's also tutoring available. I wanted to go through one more example before I give you the quiz. Now this is one that you should be able to do, but I didn't explicitly do one that contained both converting from grams to moles and then moles to atoms. So now I'm going to do that, but it's no different from what we were doing. So you should be prepared to do this. I did want to go through an example. So remember, when we're talking about copper atoms, that's our themes. But we're given the mass, we're not given the moles. So we want to know, and we're assuming in this case our penny is pure copper. That's not really true for most new pennies, but we're going to assume the penny is pure copper, which isn't actually true any longer. But if you have a really old penny, it's true. So we're given our mass of our copper, so our mass of our penny. And we want to know how many atoms. And that's all we're given. Now we don't need any more because we can look up everything else we need. So first off, our relationships. We're not given any, but we know one relationship. We know our relationship between our moles of copper and our atoms of copper, which is just going to be Avogadro's number, which is true of anything, just like, again, our dozen. Now, what we're not given is our relationship between grams per mole. But our relationship between grams of copper and our moles of copper, how could we find that? We can find that on the periodic table. So if I look on the periodic table, what I'll find is my molar mass of copper. And my molar mass of copper is 65.55. So that tells me that I have 65.55 grams per mole. And remember that the 65.55 is our grams, and that's related to 1 mole. Everything on the periodic table is our mass related to 1 mole of that thing. So now we have a relationship. We can take our grams of copper, and we have our relationship between mass and our moles, and we can convert that to our moles of copper. Once we have our moles of copper, we can convert that to our atoms of copper. And that'll give us our answer. So our solution, we're starting with, not that. We're starting with our mass of copper, 3.10 grams. What's going to be on the bottom? 65.55 grams. And on the top is going to be our 1 mole of copper. You sure it's 63? I've written down 65. Oh, it is. You're right. Sorry. One day, we put in a thing to actually have a periodic table on the wall in this room. I'm really looking forward to it. But right now, then I have to go back and forth on the computer to put the periodic table up. So that cancels out our grams. Now we're looking at our moles. And again, that's our relationship with Avogadro's number. Our moles of copper cancel out. We're left with atoms, so we can follow our units and see that we set this up correctly. So when you do that calculation, and that should be, of course, in 3 significant figures, because that's what we started with. And, of course, that's going to be neutral. We shouldn't have a negative sign attached. That makes sense with our atoms because, of course, that atoms is a big number. So you'll have a periodic table in your quiz. I'm going to pass that out to you. It's attached on the last page. So please put everything away so I can continue. Our elements typically combine together to form compounds. And there's a lot of compounds that can form. Our properties of our elements are going to be different though once they form compounds, and depending on the compound they form, that can make a huge difference in property. So for example, if we take hydrogen, which is a gas at room temperature, it's explosive, especially when you apply a lot of pressure to it. And we take molecular oxygen, which is also a gas at room temperature. And if you notice, their boiling points are both very low, clearly, because they're gases at room temperature. We can form those together if we have one oxygen for every two hydrogens to form water. And we know water is a liquid at room temperature. And it boils at 100 degrees Celsius. So notice a huge difference in the boiling point. Also, water can be used to stop combustion, whereas it depends on the compound, but if we're talking about normal combustion, water can be used to extinguish a flame, but oxygen is actually used for combustion. So just because we have the same elements in a compound doesn't mean we have the same type of physical properties. And we see that often, and as an organic chemist, of course, a big thing is natural food or organic food, which I hate that term for food because all food is organic. If it contains carbon, it's organic. Another big thing is mercury in vaccines. But just because it's mercury doesn't mean it's necessarily horrible for you, because the form that's in vaccines has never been shown to have adverse effects. Because it's not the same as elemental mercury, which clearly you don't want to swallow. So a lot of people don't understand this concept that just because an element is in something or a molecule is in something doesn't mean that's going to react the same way as an element in another compound. How do we predict these things, these reactivities? There are ways. Some of this is going to be beyond this class. As you go more into chemistry classes, you'll be able to predict some properties, predict reactivities, and we're going to kind of start getting there, and then you get more there in organic, and then if you are a chemistry major, you really start looking into those kinds of things. But as of now, just understand that when we form compounds, we have totally different properties than our elements. We've already talked about that a little bit before, the difference between elemental chlorine and our chloride ion. So as far as classifying our elements, there's two main types of elements. We have our atomic elements and our molecular elements. Our atomic elements are elements whose particles are single atoms in the elemental form. And that's most of the elements. But there's a lot of elements that are multi-atom molecules. For example, H2, N2, O2, and our halogens. We call these molecular elements diatomic molecules. Di means two. Atomic for atom. So molecules that have two atoms. Pretty straightforward for the naming. This is how you would find these elements in their natural form, N2, O2, H2. There's a couple of molecular elements that are more than just diatomic. For example, P4 for phosphorus in its elemental form. We're going to have 4 molecules of phosphorus. Sulfur likes to exist as S8, and selenium as well as S8. So you should know those. It's not that many to know. You should know which ones are diatomic and which ones are polyatomic. Poly just meaning more than 2. Otherwise, most of our other atoms on the periodic table exist as atomic elements, which means just that atom. And later on, we're going to really delve into why something like hydrogen likes to exist as H2. But as of now, we're just kind of knowing them. Now, when our multiple elements come together to form compounds, we form chemical bonds. And that's how our atoms are held together. So there's some sort of force of attraction. We will often show them as lines or things like that, but we'll talk about what causes a bond, and typically it is that electrostatic attraction. Meaning, again, positive and negative charges interact. So the bonding attraction comes from some sort of attraction between our protons and our electrons. And depending on the type of bond, that changes slightly. It's going to make me do that thing. Oh, yeah, it did. So there's two general types of bonds as chemists that we talk about. And those are the two we're going to really focus on in this class. And that is ionic and covalent bonds. And there's a pretty large difference between ionic and covalent bonds. So ionic, ions, pretty straightforward, means it's bond between two atoms that have charges. So our attractive force results from a positive charge and a negative charge being attracted to each other. For example, sodium chloride. That's our sodium ion, forms a positive one, and our chlorine ion forms a negative one, and those two things being attracted to each other. What happens in an ionic bond are one atom is going to give up its electrons to form a cation, and the other atom is going to accept those electrons to form an anion. But the main attractive force that causes the bond to happen is the attraction between our positive charge and our negative charge of our two anions. So that's why it's an ionic bond. They generally form when metal atoms bond to non-metal atoms. So what we typically see, and a good way to determine if it's an ionic bond or not, is look, is it a metal and a non-metal bonded together? They can be simple or they can be polyatomic. So for simple, an example would be the chloride ion interacting with copper, things like that. And then we'll talk about the ratios of how they exist. Polyatomic ions are atoms that have multiple atoms that form a molecule that have an overall charge. And these particular type of atoms, polyatomic anions or cations, there's only one cation that we'll really talk about in this class. They are a mixture of covalent bonds between our non-metals and then having a full charge. And we'll look at that in a little bit more detail in a couple of slides. Now, covalent bonds happen when two atoms share electrons, as opposed to forming a full positive charge and a full negative charge that attract. Our two atoms instead share two electrons. So we don't form a full charge in those examples. So those typically happen between our non-metals, bless you, and that's why most of organic chemistry is the study of covalent bonds. Though ionic bonds do come into a lot of play when we're talking about those. So the attractive forces that we're looking at is the protons from one of the atoms being attracted to the electrons of the other atom. Because remember, the protons, though they don't move, they're still there. So they can still be attracted to the electrons in the other atom. And those attractive forces cause a share bond. There's also an issue, though, with covalent bonds that we have repulsive forces between electrons of one atom and the electrons of the other. And in organic chemistry, we focus on that a bit more. We'll look at that a little bit in chapter 10, but that's more of something for organic chemistry that we'll focus on. Bless you. So covalently bonded compounds, we typically call them molecular compounds because they form molecules. And usually we say molecules when we're talking about covalent bonding. Sometimes you'll hear ionic compound or ionically bonded atoms called ionic compounds. And we're going to look at the difference between those two types of bonding compounds. So looking at this one, which has both ionic and covalent. So this first one, sulfur is a nonmetal, oxygen is a nonmetal. It's only attractive forces between nonmetals. So in that case, we just have covalent bonding. Same thing with CF4, again, all nonmetals. Sodium chloride, we have a metal and a nonmetal, so that's ionic. Na2SO4, we have a metal, and then we have these nonmetals. So the sulfur and the oxygen are going to be bonded covalently, but they have an overall charge which is attracted to our metal. So this particular overall molecule has both ionic and covalent. And P4O10, again, all nonmetals, all covalent bonding. So that's what we're looking at. So ionic bonding is bonding between atoms that have charges, full charges. So this is just a little example of what I just talked about. So our elements can be broken into atomic and molecular, whereas our compounds are typically talked about as molecular compounds, which are nonmetals, and are ionic. Now notice, if you look back at your examples of your molecular elements, notice it happens between elements that are nonmetals. So there's still covalent type bonding. It's just a covalent bond between two of the same atom. So BR2, F2. If you look back at that list, you'll notice that they're all nonmetals that behave in this way, including hydrogen. So notice that molecular is usually used when we're talking about covalent bonding. And this is just a representation of the difference between our molecular compounds and our ionic compounds. And we'll break that down a bit more on Monday. So just before we leave today, aluminum, we would classify that as an atomic element. Aluminum chloride, however, is an ionic compound because we have a metal and a nonmetal bonded together. And we will talk about the charge and things like that next time. Cl2, now that's only one atom. It's two chlorines, but it's only one type of element, so that is a molecular element. Acetone, we only have nonmetals bonded together, so that's a molecular compound. The terminology is distinct between these two, don't mix it up. Carbon monoxide, again, molecular compound, we just have nonmetals bonded together. Cobalt, that's just a metal, it's just an atomic element. So we're going to talk about representing compounds a little bit, and we're not going to focus too much on just this, just a quick example of representing. And then we're really going to break down our difference between ionic compounds and molecular compounds. So you guys have a good weekend. If you're going to the gate, we'll be doing chemistry demonstrations at Family Day, so stop by our table. Not exactly sure where it is, but you'll find us. Yes.